Okay, well, I'm going to go ahead and get started. So today I'm going to be talking about convolutional neural networks, giving kind of an introduction to those. This is geared towards people who, maybe you've played with them or you've heard about them. It's very much a introduction to them. And then we'll go ahead and work through a little tutorial example I put together, and you can run it in Colab where you'll have access to GPU, because for convolutional neural networks, you definitely want GPU. It's like crushingly slow if you don't have that. All right. So before I start, you can see kind of my general plan for the rest of spring. I am going to be inviting more guest speakers. We had 2 guest speakers the last 2 weeks, and I'm going to invite more, so I may tweak it a little, but you can get kind of an idea of what the topics are. I'll post these, and hopefully you're getting, if you've signed up via Zoom, hopefully it kind of tells you what the topic is. I might not have put the one in for this week. All right. As always, you can toss questions in the chat. I will try to watch those. But you can also, I think if you raise your hand, I may hear something, but I'll try to be watching the chat here. Okay. So let's see, let me give you this website. Yep. So that's the website that we're on. And if you click onto the topic for today, it will take you to this tutorial that we're going to go through eventually. Okay, here we go. So this is what we're going to go through. We'll see through the time. I know I'll get through the CNN and the boosted regression tree. And maybe we'll get to the UNet. If not, you'll be able to run through the UNet yourself. Okay, so let's go ahead and click on this, open up in Colab. So that's going to open in Colab. You need to be logged into Google. And so Colab is all set up to run things in Python. We're working in Python. And nicely, it also has like TensorFlow and I think PyTorch, and it's set up to work with GPU. So you don't have to install anything, which is really great if you're trying to learn this. Okay, so but by default, it's going to start you up with CPU. So we need to switch to GPU first. So let's change run type. And then you can see you can choose this T4 GPU. I'm just logged in on the free version. It's not like a premium at all. But you could pay money and get more, but this is what they give you for free. All right. So we'll save that. Okay. So if you're following along, you want to, learn by doing, go ahead and do that. Open that up and change your run type to GPU. Okay, let me see if I can keep that chat over here in case you guys have questions as we're going along. All right. So, so this tutorial today really follows up nicely on our boosted regression trees. The application is a little bit different, a bit closer to what I did the first week where I was predicting chlorophyll. Once again, we're going to be predicting chlorophyll the same way I did the first week where I was using a boosted regression tree. But what's going to be different now is we're going to be using a really simple little convolutional neural network to do the same thing. So I'm going to jump right down here. So what's the goal here? The goal is that we have something we're trying to predict. In this case, I'm trying to predict chlorophyll at a pixel in a map. And I'm going to be predicting that with some variables. In this case, I'm going to be using the following variables. I'm going to use SST. I'm going to use salinity, going to use season, and location. So those are the only things. Oh, I guess I do have an ocean map, which kind of tells me where land is. That's actually not so important for the prediction. It's important for identifying missing values in your layers. Okay, so just to like orient ourselves, that's the objective. Let's see, I should have a picture here. Let's just scroll down for a sec to show you. Okay, so this is the goal. We've got a true, what you're looking at here is chlorophyll. And we have chlorophyll, each of these is little pixels. You can kind of see that they're pixels. And what we're going to do is we're giving it information about, at that pixel, SST, salinity, season, location. And then we're going to try to predict the chlorophyll. So we know the truth, and then we're going to try to predict it. And this shows a prediction of what that chlorophyll is. This happens to be with a convolutional neural network. I know, predicting chlorophyll just with SST and salinity, not the best, but this is for learning purposes. It doesn't do horrible. Okay, so let's jump back up. And I want to back out and talk about like what a convolutional neural network does, because it is fairly different than like a boosted regression tree or like a multivariate linear regression. So let's jump here, and it should, if it works, yeah, here we go. All right, so let's think about I'm using a picture of SST here, but I am predicting chlorophyll. Okay, but let's pretend for a moment that we're predicting SST. So here's the thing that I'm predicting, and so it is a grid. It's gridded data, and at each pixel point, there are these values of SST, and I'm trying to predict the value at that pixel. And what a convolutional neural network does is it's going to take into account the spatial context. So like a boosted regression tree, we would use this pixel and the values of like SST and salinity at that pixel to make a prediction. And what a convolutional neural network is going to do is it's going to say, okay, it's okay, back up a little bit. So I said in the beginning, that I'm predicting, that I was, in this example, I'm predicting the SST, but that's, as I'm talking about it here, sorry, I'm going to be talking as this is one of my explanatory variables, actually, in the way that I do have it in the model. So this is one of my explanatory variables, but I'm going to be using this to predict chlorophyll. So this is my explanatory variable. In a BRT, a boosted regression tree, as we did the last 3 weeks, we would be using this value at SST and matching that up to the chlorophyll value at that pixel. What's different about a convolutional neural network is we take into account a small spatial context. And what's interesting about this is that it's not like exactly like you're thinking about it as like the neighborhood, like in a BRT, we could input into our predictors all the neighboring values. Like we could certainly do that. But what a convolutional neural network does is it tries to pick up these spatial patterns and these small scale features. So let's look at this SST image here. And so our eyes can quickly pick up a few features. So one, there's a front. So notice green, yellow, green, reddish. So that is like green here and yellow, red here. That is a spatial feature. That's like a front where it changes rapidly. Over here, here's another spatial feature. It's uniform. This over here is kind of similar, kind of uniform also. We can also pick out gradients. Let's see if we can pick out a gradient here. So where do we go? Oh, here's kind of a gradient right here. So you can see it's kind of green and it's getting lighter and lighter. So that would be like a left to right gradient. Gradient going this way. We could have gradients going this way. Gradients going diagonal. And a convolutional network is training these features that pick up those things. So in a convolutional neural network, the convolution is, in the example I'm going to be showing, we're going to do 3x3 convolutions. So there's these little convolutions. And it'll look like this. It'll be like a little matrix, and there's numbers in it. And the combinations of these numbers will detect different types of features. So like this would detect a line. This would correct kind of a little blob. This would kind of detect a north-south front. So all of these little things will detect different types of features. And what we do in our model is that we will have a series of layers, a series of steps that we go through as we're fitting the model. In the first step, we're going to be defining a whole bunch of these little features like this, fronts and lines. You can imagine a front this way, a front that way, a front that way, lines this way, lines that way, lines at an angle, all those kind of little things that we could detect. And it's going to kind of search through and find the features that appear in your explanatory variables. So like the features that appear in my SST would be maybe different than what appear in the salinity. It's going to find features for both of those, whatever explanatory variables you have. And then, okay, so here's like the key kind of next step that happens is that it finds those little features, and then, so it takes this thing, okay? It's a 3x3 little matrix. And then it's going to go to this image, and it's going to multiply that little matrix by all the numbers here. And then it's going to slide over here and multiply it by all the numbers there. Oh, it's going to multiply it and then sum them up. So it's going to get like a value for that, a value for that by doing that multiplication and summing. It's going to do all of it. And it's going to do it for all 64 of these little feature things. And what's going to come out, what it's going to look like after you do that, it's going to look like, this is for a bird, but it's the same idea for my SST example. But after we do all that, you're going to have 64 of these little maps that look like this. So we've gone from my SST to 64 versions of the SST, but it's a SST where I've multiplied it by these little things. And now, so it's a little hard to make out here because it's so tiny. But like if you have one of those convolutions that picks up lines, you're going to kind of see little lines in that map that's associated with detecting a line feature. So you have all 64 of these. And then in the next step, you're going to take those. Okay, so you've done that first step. You've created these, using those little features, you've created now 64 new maps based on your SST. And now you're going to take that And you're basically going to ask, how do these local features that have now encoded as these 64 new maps combine to explain our output, in this case, chlorophyll. And so our new convolutions are going to be, in my example, so it's going to be our 64 of these, and then I have a new 3x3. And then there's one for each of these, each of those 64. So that's what's happening mathematically, but like how you can think about it is that it's asking, how do all those little local features combine and explain something bigger? And mathematically, what you're doing is you're taking these 64 little feature maps, and then you're taking this new convolution. So we're now in layer 2, new convolution. It's 3x3, but it's one for all the layers. And you do the same thing. You multiply it all by here, and then you sum it up, and you get 1 point. Move it, sum it up, and you get 1 point. And when you're done with that, your model is going to use that to make this model output that you're predicting, and you're going to compare this to this. Now, obviously, the first round, when it goes through the fitting, it's not going to look like that. It's going to look awful. But as it tunes it starts to learn things. It's going to get better and better. And if your model kind of works, it's going to get as close as it can. All right. I hope that helps a little bit explaining this. There's so much information out there in the web, so many videos you can watch. So go explore those if you're interested in this class of model. You learn a lot, but hopefully that little introduction helps you understand a little how these are working. Okay, so now we're going to go through on Colab, actually, like, okay, how do we fit one of these? Try to demystify it a bit. So here are the modeling steps. You're going to load in the data. In this case, what I need are my maps of the thing I'm predicting. So it's chlorophyll. And then I need my predictor variables. I need my maps of SST. I need my maps of salinity. I also need this ocean mask. And I need this cloud mask saying where clouds are occurring. I happen to use data that does have clouds in it. So this is something that I pre-made as a ZAR file. This is a cloud native format, makes it really easy to work with. You'll see, you can just load all this in. So that's what we're going to be doing. We're loading in these layers of predictor variables. They're maps, basically. And it's for 10 years of data, or 20, something like that. It's a lot of years of data. Monthly data. I think it's monthly, or is it daily? No, it's daily data. Okay. So let's go through, let's talk a little bit more about the predictor variables. So we have sea surface temperature and salinity. Those are these maps. I also used in the model seasonality, which I encoded as a sine and a cosine, using the day of year. This is a pretty common way to include seasonality. I also, in this model, this happens to be predicting chlorophyll in the Indian Ocean, and there's Africa on one side, India on the other side, and the patterns in chlorophyll are really different in these two regions. So I wanted to be able to encode location. And then also just kind of for an example in a tutorial to show you how you would encode location. Using spherical coordinates for location is a very common way to do that, and gets around problems with using lat long to describe location, because lat long is not like a uniform the distances associated with the longitude change depending on where you are in the globe. And you can, so using a spherical transformation is a common way to deal with that. Okay. Dealing with NAs is a big hassle in convolutional neural networks. Once you've done it a few times, it's not such a hassle. You figure out how to do it. But when you're beginning, it's something hard to get right. Fortunately, like chatbots are quite good at it. If you explain what you're trying to do, they'll probably steer you in the right direction. Though if you are doing your very first CNN and playing around to learn, I would say use data that does not have any missing values. So my data does have missing values. It has two kinds of missing values. First off, there's no chlorophyll on land, so that's all NA. And then I happen to be using a product where there are clouds, and so there's a cloud mask. So what I need to do is I need to tell my model where these NAs are and say, don't train on those. Definitely for the clouds, I don't want it to train. For the, I'll have to see when I get to the code exactly how I dealt with the ocean mask. Sometimes you'll use the ocean mask to learn the land, learn coastlines, because what it learns is that, oh wow, there's a really sharp transition, land, water, and it can learn those transitions, so it can learn that it's up close to land, and that can be helpful sometimes. Okay, and then of course we need our Y response. In this case, is chlorophyll. So I have a whole thing here on how you have to deal with NAs. Little section if you want to modify this tutorial for your own data. Okay, so next we're working in Colab. It has most of the libraries we need, but there's a few it doesn't. We don't actually use Earth axis, but these helper functions I'm going to load do have it, so I had to load that. We are going to be using ZAR because the cloud data, this Indian Ocean data set, is using ZAR, and then it's in a Google bucket, and part of the NOAA NOD program, so that's why we need that. So we can do that and run anyway. Okay. And this is going to install for you. Everything else that you need is installed, and importantly, like TensorFlow is installed. Well, that's really important and really helps you learn, because it can be a hassle to set that up sometimes. But it's all set up for you. Okay, are you done? Okay, good. Great. And then we're going to import our libraries that we need. And then we're going to import the TensorFlow modules that we're going to need. This is just some things to make it a little quieter. TensorFlow has a very voluminous log span. And then these are the, actually I didn't use batch normalization or dropout. Those are really standard things. I'm just going to use sequential and convolutional 2D. So convolutional 2D is what we're going to be using to do a two-dimensional convolutional neural network. So we're working on 2D data. CNNs are not just for 2D data. You can definitely do them for 1D data. If you're working with 2D though, you use this module here. So go ahead and do that. I don't know why that's taking quite so long. Okay. I wrote a bunch of like custom functions to do the predictions, and you can see them. They're in this code right here. But rather than having them in this tutorial and kind of filling that up, I have them in this repository and I load them like so. Okay. So in this next step, we are going to load in our Indian Ocean data set. At the end of this tutorial, it does what's called a UNet model. And for a UNet model, you need the number of pixels to be even. So there's a little like extra happening here to make sure the pixels are even. It's not necessary for the CNN, but this is prepping it also for interesting, gap free. Okay. I was pausing there that it's gap free. It's not entirely gap free, it's sort of gap free. It does have these clouds in certain situations. So this is taking a little while. I'm not sure why it's taking so long, but it doesn't take forever. It's just reading from a cloud bucket, but ZAR should be fast, but for some reason it's taking a little. Okay, so what is this doing? It's loading in this data set and it's preparing it for us a little bit. The full data set has lots of different variables in the Indian Ocean, and I'm going to pull out the SST and salinity. I'm going to pull out this product here. It's a chlorophyll. Like I said, it says gap-free. It's not really. And then I also want my land mask, and I put them all into my data set. So instead of having the full thing, I'm going to take a subset of that, do a little renaming, and do a little cleaning here. This is starting, I think, in 97, and I remove the early years that just had NA. So it's a little bit of data cleaning that's going on here. A little bit of fixing up my ocean mask. And then importantly, here is where I add these spherical coordinates to the data set. So I'm creating an X-array data set and I'm adding on a few things. So this function here is what adds on my spherical coordinates. Going to use lat long and add that. And then also my seasonal. So it's like a function. Yeah, so how am I creating the mask? So the mask often will come with products that you're using. So I'm using for the chlorophyll, this is a product from Copernicus, and their chlorophyll products inside the data set, it comes with a mask. It's their land mask. And what you'll have to do when you're working with a data set, you would look at, does it have a mask? And you're going to have to open it up and look at how they define the mask. Like sometimes it'll be zeros and ones, other times it'll be NA and 1. It really kind of varies. So there's a little bit of like looking at your data and understanding their mask. If that doesn't work, what you can do is there are various tricks you can use. One trick that people will use if they're working in the ocean and say the product has SST, but it doesn't have a land mask, you could define wherever SST is NA, that's land, because they're not going to have sea surface temperature over land. If all that fails, then you're going to have to do a bit more work, because you're going to have to somehow combine a mask from something else with your product, and then you're going to have to make sure they're on exactly the same grid. But fortunately, a lot of products will already have a mask in it that you can use, or a variable that you can translate to a mask. Or you find another product that's on exactly the same grid and you grab its mask. Okay, so the next thing that I need to do, so now I have this data set, and here's my data set. You can see what it's gotten there. It has my latitude and my longitude. It's got my time steps, and it has all these variables. And let's look at the dimensions. It's got time, lat, long. That's what I want, time, lat, long. So these are my spatial layers. Everything is matching up here, beautiful. My ocean mass does not depend on time, it's just lat, long. My spatial coordinates also lat, long. And all right, so you're looking at the seasonality, you might wonder, well, hey, why would you have this also be a function of lat and long? Because season does not change by lat and long. This is a requirement for including this feature in the model. So it would have had to expand it out to lat long anyhow, and I just do it ahead of time. Okay, so that's what you need your input to look like. And the next thing is that you're going to split that into your training set and your test set, and then a validation set. So there's various standard procedures for this. I wrote my own, but it's a pretty, like, just a standard thing. You're just grabbing these samples of your data and splitting some up as your training and some as your testing. Yeah, so like another question about that mask that you use. So yes, there are high resolution masks out there. Whether it's going to be useful for your application, like in the way that I'm using it, maybe not, because you need to have whatever data that you're training with, the grid that is using, to be the same as your mask. They all need to be on the same grid. So like this, like it's all one data set and it's all the same lat long grid. That is a crucial part of this. Okay, so we go here. Okay, so what is happening here? To make this tutorial go fast, what I did is I'm loading the data set into memory. It's an advanced topic to show you how to fit convolutional neural networks to batches of data, so larger than memory data. In this example, I'm specifically using something that I can load into memory. So that's fine. Okay. So for this step, this is going to create these NumPy arrays. And so I have to have it loaded into memory for that step. So this is what's happening. I'm creating a bunch of NumPy arrays. These are NumPy arrays. So now I have my NumPy arrays, and this is what TensorFlow is going to want in the next step when I'm fitting it. Okay, so now let's create our convolutional neural network model. I'm using Keras here, and I showed two ways to create this simple model. I will say the chatbots now, they know these, they know TensorFlow and Keras really well. And if you're doing something really straightforward, they're very helpful. So just lean on those to help you learn how to construct these. Okay, let's just walk through this simple example here. So I am going to use a sequential model. That means I take my layer 1 with all those 64 features, and that's going to flow into the next layer, putting those 64 features together with a new convolution. And then the next layer, it's going to take that layer 2 convolution, sum it all up, and make a prediction of my chlorophyll. So that's what that's saying. because that's what I'm doing. I tell it its shape, it needs to know that. And here's my layer 1. So layer 1 are those 64 features and those 3x3 kernels. The next one is going to be 32 filters, and these are going to be 3x3 by 64 actually for each of these layers coming out of this. And it's 3x3. So it's going to get those all together. And then the last layer is what is producing my prediction. So I want to make one prediction. So that's why I'm predicting 1 here. And then it's linear. So this is like a, oops, where did I go here? Like kind of a really classical example of a simple 2-layer CNN to make a prediction of one thing. I'm predicting just chlorophyll. This is the same model, just written a different way. So it doesn't really matter. Okay, let's go ahead and do this one. Okay, there we go. Okay, so I define the model. That's how you do it. And then when you are working with data that have missing values, you have to create a custom loss function. And that's what I'm doing here. And it looks a little hairy. Again, chatbots are pretty good at helping you do this. If you take this code and you kind of explain what you do, it'll probably come up with a really decent code to show you how to do it for your application. The basic idea is I don't want it to be learning chlorophyll, which is going to be 0 over land. Don't want it to be doing that. I need to tell it not to do that. So that's what that custom is. So, you know, I debated whether to include this in a simple tutorial, but the fact of the matter is that, you know, when we're doing things over the ocean, we have to include these custom loss functions all the time because we always have land. Okay, so we've got that custom loss function, and now we fit the model, and this is what it looks like. So it's pretty simple. So here's my function that created that tiny CNN, and all it needed was the shape of my training data. And then here's the part that compiles it. And we just run it. Wait, no, don't do that. Why did you do that? Oh, I did do that. Oh, come on. Fine. Okay. Guess I did want the second one. Okay, there we go. All right. So what this is doing is, you know, each of those 3x3 convolutions is a number it needs to predict. So there's a lot of numbers that it's tuning to do these predictions. And it's going to do it in these epochs. So you think about it like the model is like optimizing across number of steps. And it's tuning all the numbers in, so like, let's say here, you know, all the numbers in here, like it's got like 3x3 by 64, a whole bunch of numbers there. It's tuning. These are also, they're not ones and zeros, they are floats. So it's tuning all of those also. So a lot of tuning. And then it's using the validation. So it's holding some data out to compare against during this training process also. Okay, so it just keeps tuning things. It's trying to decrease the loss function. How's it doing there? Yeah, it's slowly. Okay. Now, if I did not have a GPU for this, it would take forever. Okay, it's not forever. It would take 5 minutes or so. So it would feel like forever. But with GPU, it's these types of models are much faster. I'm not sure if I had a stopping here. Yeah, it looks like I didn't set up stopping. So you can set up stopping to say, hey, if you've fit pretty well, go ahead and stop early. For this simple example, I didn't put that in there. You can see it's kind of gone through there. It went through all 50. And now I'm not going to save this part. Let's go down here. Now we're going to plot. We're going to use the history, and we're going to look at our training and our validation loss. So there we go. That is, what we want to see. We want to see that the training loss is going down over time. So that's good. It looks like it's still going down. Maybe I could, run this a little longer. Now what we want to do is compare to our test data set. So we can take a model and we can evaluate it, and we give it the test that we created. These are these NumPy arrays that were created higher up, and compare it to our test. So that's our test loss. I find it most useful to compare maps. Like if I'm trying to predict something that's a map, I find it helpful to look at the truth and then the predicted. The code for that is a little bit hairy, so I made one function for this, and I keep this in a Python script, and then I'll load those scripts. So I did that earlier in the notebook. And what we can see here is, so what it did is it picked a date that I didn't use for predicting, and it gets the variables SST, salinity, locations, and the season from that, and then it uses that to make a prediction for all the pixels. So you can see here is the actual, and here's the predicted. So one of the thing, can the loss increase as you add more? Well, you can start overfitting. You could, but that would be a little unusual for it to increase. You want it to keep decreasing. It could not decrease though. Like it could be that your model is so bad. Interesting. Yeah, I'm not sure why it would increase. I would have to poke into that more. It shouldn't do that. It should keep going down. It might, there's some variability. You can kind of see here, like here, yeah, sure, it increased here, but then it goes down, increase here, and it goes down. And then at some point when it kind of levels off, it should just be kind of fluctuating up and down, up and down, up and down.
Yeah, Eli,
So,
sorry, Eli. At the
yeah,
end, in my case, it
uh-huh.
just jump it back.
Oh,
I mean,
strange.
it's a strange the map. I mean, the figure that I get at the end, before the 50 epoch, it just went up,
Yeah, no
and I was
idea.
like,
Yeah,
"What's going on with this one?" Okay, no
yeah,
worries. Sorry about that.
yeah. Run it again. It is a stochastic process. Yeah, and thanks, Ricardo. Yeah, it can, if the model starts to getting overfitted, then it can start to increase for sure. Okay, so let's look at the predictions here. And so this is a feature of CNNs, is this kind of smudging or smoothing. That you see here. You see it's kind of got like the overall picture. That's cool, but it's losing some of the details here. It's kind of like smudging it out in a way, like, some of those like spatial averaging models that we use do that. It's kind of doing the same thing there. And that's a feature of the CNN. We can look at all the months here. So I took, I think is probably the first day of the month here. Oh, I picked day 10 of the month, made a little function that does that. And you can see how it varies. Because I include season, it is learning that patterns could be different in different times of the year. And So you can see here, it's kind of, yeah, not terrible, not terrible. Kind of picking that up. So, it's getting these broad patterns for sure. It's like not terrible at all. Here's an example of those missing values that happen. They happen during the monsoon when just like the satellite never ever sees this part of the ocean at this time of year. But you can see it's like it's not terrible. Getting the basic. So we can also do things like look at metrics over times of year. This is, you can run that code if you want. I wrote a little function that does that. It gets your R squared, gets the bias. This is a spatial similarity metric you can get. This is the mean absolute error. What you can see, if we just look at like R squared, you can see it's got this dip. This is across years, different colors are different years. The purple is what was trained on. You can see that even with the training data, it really struggles right here, July, August. And this is, first off, it's a time of year where we do have like no data. So there are just these times when there's just no data. So that's kind of a problem there. And then I think that's probably what the problem is that there tends to be days when there's just more no data, or it just may be that from year to year, like what's happening during the monsoon, it's just much more unpredictable. Could be. Then there are other times of year where the R square is very high. It could be that, it's just easier to predict. There's more uniformity, say. So I thought it would be interesting also to compare to a boosted regression tree. That goes a lot faster, and we can just take a look at that. So we can use the exact same data that we used to train the CNN, exactly the same, and we can do splits for a boosted regression tree. I put this in the Python file. You'll find the link to the Python file at the top if you want to see what that looks like. And for a boosted regression tree, we don't need a GPU, but I'm on the GPU, so I'll use it. It doesn't really speed things up. It's fast. So that was training. And what does that say? Train fifth month. Oh, it says train. Yes, it is training. So it's taking the splits and it's training the model. You can see it did that in 8 seconds. I'm not going to run this one because this is slow, but I will run these. So this compares the CNN and the boosted regression tree models. So it's taking this year and one of the days, I think first day of the year. There we go. And now we can compare them. And we can see that, honestly, the boosted regression tree is not all that different, honestly. It does have a few kind of features that would cause me to move towards a convolutional neural network. One, and this is not uncommon for boosted regression trees, the way that it's a tree splitting thing, you can, even though I'm using spherical coordinates for location, you get this kind of banding. Do you see that banding there? That's the banding. Like that happens in boosted regression trees because of the way they do these like hard splits on your location parameters. You're not going to see that in your convolutional neural network. But other than that, overall, the boosted regression tree kind of does okay. I mean, definitely. I mean, in a way, I wouldn't say that it's doing any worse. The boosted regression tree is not doing this spatial smoothing. It's independently estimating each pixel. So it doesn't have the same tendency to kind of smudge things out that a CNN does. It's hard to kind of see that. Maybe you can kind of see it here where it's got a little more of these extra little features here that may be because it's a boosted regression tree. But in general, they're both picking up some of the same patterns. Okay, I'm going to stop there before I show you guys or talk a little bit about UNet models. See if there's any questions. Longer runtime to run the BRT. Oh, that's very strange. It's still running.
In my case, it's still working, still doing. And now it's gave me something good. Now it took about 2 minutes something. 2
Oh,
minutes
that is
50.
strange. Yeah,
Yep.
mine ran like you saw, it ran like in 8
Yeah,
seconds.
I was
Yeah.
like surprised. That's why.
Yeah.
I just had a quick question.
Uh-huh.
I was just curious with that simple example with SST, and you were kind of showing that there's these gradients of the pixels, and you were like kind of looking at neighborhoods where it's like, oh, it's pretty uniform here, and then the pixels change pretty rapidly here towards the front. But it also seemed like within a pixel, yeah, right there, some of those pixels where it's yellow within the pixel, it goes from green to yellow. So there's variance within. Does it use that information, like the variance within an actual pixel of how things are changing? Yeah. Or does it just value for that pixel?
Yeah, so this is the danger of using AI to create your gridded
Oh,
SSP image. No, in the actual image, each pixel would be one color.
okay.
So
Okay.
the actual data looks like this. So it's one color. Yeah.
Cool. Thanks.
Yeah. Typically your pixels are not going to be quite that huge. They're pretty. Well, I guess it depends. They may be like 4 kilometer by 4 kilometer. I guess that's kind of big. Yeah. But it would be just one value for the pixel. Okay, so I want to talk a little bit about UNet models because they are very popular within the earth sciences. You may have heard them before if you've, watched talks or seen papers using convolutional neural networks. So what is different about a UNet model is that, so in a convolutional neural network, it like learns these, let's go back here. It learns these really small 3 by 3 features. So that's pretty small, 3 pixels by 3 pixels. And then it asks in the layer 2, it says, how do we combine those really small local features into this larger feature? So how we like make some combination of those 64. We're gonna weight all those 64 and sum all that together to get this one weight that's combining all these different local features. And that behavior will tend to cause these like kind of smudged images. And UNet models, they do that part. They find that it's like, oh, how do we take these small features and put them all together? It does that. And then it has a step that's called a decoder step, where it says, all right, so now I know what kind of the big picture is. Now let's take that and then decode back into the fine features. So the CNN takes you to the big features and it uses the big features to get your prediction. The UNet doesn't stop there. It takes that and then it does this decoding back to the fine. So if you are doing something like you're trying to take a fuzzy image and make it sharpen, you will use a UNet model. You want to look at the image and pick up, oh, okay, I get it. Okay, that's kind of a bird. And then you take what the model knows about the fine features, then to make this prediction with a bird with all the fine features in it. So in like an ocean situation, a common way I've seen this is if you're doing like downscaling. So let's say you have a remote sensing image that is 4 kilometers by 4 kilometers, but then you have some more data that's like 1 kilometer by 1 kilometer, but you don't have a whole lot of the 1 kilometer by 1 kilometer. So you're going to train this convolutional neural network on the 1 kilometer data. And what it's going to do is going to learn the finer scale patterns. And then you can use the model to take your 4 kilometer data to create new 1 kilometer grids. So that's a real common application of UNet models. So this is a really simple example of one where the first part, it has this encoder part, and then it has this decoder part. This example that I got here, it's a tiny UNet. I just picked something that was like a vanilla UNet architecture, just to show you that it's not that hard to fit these. So we can take that. So we have our tiny UNet, and it works exactly the same. So what it needs, the model, it needs its shape. That's our UNet model. And then it's the same thing. We pass it in. All the functions are the same. The loss is the same. So it's working the same. What's different is that we are defining the shape of the model, the architecture of the model differently. And so, we can do that. And it's going to chug along. There we go. Doot. This is going to take a little while, but I'll show you the end result. So I created a function to compare these. And, it's not like, I would definitely need to be tweaking this model a bit. It's not like crazy better. Like, it's not getting all the finer features that I want. So, I'd have to explore more of why it's not getting more of these finer features. And it's honestly, I can't tell you whether or not it's getting the finer features better. It looks awful similar to the CNN. But I haven't like played a whole bunch with the UNet model. I think I just need to play with it to get a little better. But you can see it's it does different in different situations. Again, it's hard for me to say, is it better? Is it getting more the local detail? It's probably a stretch to say that. All right. I'm going to stop there. Hopefully seeing some of these models in action demystifies it a little bit and will inspire you to, play around with it. Colab is a really great tool, just for free. It's going to give you the GPU, and importantly, everything is just set up. So you're going to be able to just run examples. I found it really helps with my learning, just to be able to find other people's tutorials and jump into Colab and be able to run them and putz around.
So Eli, question quick. Thank you very much for all this. But if someone asks you about what to use for chlorophyll, which kind of model, from your experience now doing BRT and doing the boosting the tree and doing CNN, doing UNet, how you feel about when you compare? I mean, I know this is not the perfect example you have here, but I think you can see something in there already. So which one feels like more, I mean, there's a trade-off there because if you don't have GPU, you're not going to be able to do CNN. But I think BRT is still, you can do that. So just dropping that question there. I don't know if you have any specific question answer to that.
I think for me with the BRT, I really don't like the striping that occurs with the location, and that's a pretty common thing to occur when you have boosted regression trees with anything that's about location in it because of the way the tree splits. So that in and of itself would take me away from the boosted regression tree.
Hmm.
And I think that I'm interested in the way that spatial patterns, things like fronts, things like swirls, things like eddies, help us make predictions. And we know these things should be important for chlorophyll, say, or whatever we are trying to predict. And so, I'm attracted to models that allow me to incorporate that. I'm using really tiny little CNNs that have these little tiny, like this 3x3. I would need something, I think, kind of larger and think a little harder about how to get something that's capturing the fronts better, these larger scale fronts. So these tiny examples didn't quite get it.
You got that. Yep.
Yeah.
Thank you. I think the other one, I mean, what you're going to do, you random maybe all, and then do some akaiki or comparing those models and see what, other way to think about if you are running two different models with the same type of data. So you can
Yeah.
probably try this
Yeah. Yeah.
BIC or, yeah.
Yeah. I think a really nice thing about boosted regression trees is they tend to be really easy to fit and
Yep.
they fit fast. So
Mhm.
it's worth using them as a null model to to me, it feels like to kind of keep myself honest and not overinflate the kind of value of using a more complicated model, a convolutional neural network, right? If the boosted regression tree does almost as well, that says to me, oh, there's something really basic about these variables that's capturing what's going on. And I didn't need all that spatial context. Or it's telling me, oh, I haven't quite set up the model that's to capture that spatial context yet. All the explanatory power is coming from just the values of my parameters and not the spatial structure of those variables. So it tells me, I need to change that CNN a little bit. You maybe make it bigger, maybe rethink the architecture some.
Mm.
Yeah.
Yeah. Eli, you mentioned something because I'm interested on that downscaling, and you mentioned UNet can be perfect for that. Um, so you had some experience with it, or you've seen some papers using the UNet for downscaling?
Yeah, I do have first I've seen a lot of papers doing that,
Mm.
and then it was a one of my interns did an Ocean Hack Week project. Let's see if I can find it. Past Ocean Hack Week 2020 Bigelow 11 projects. Upscaling. Yeah. So this was the project,
Yeah.
and um so I sometimes find like rather than looking at a paper where they've solved everything, I can sometimes find it more helpful to look at somebody's like early
Mhm.
tutorials or like notebooks where they kind of got the idea working. That'll help me apply it. So I can put
Nice.
this the chat. This is the experience I
Nice.
have.
No, no, nice. I like the way that way. I always like, because that's what we do, right? I mean, we post things in
Yeah.
GitHub, and sometimes nobody, that's helpful because now you know exactly, what is the experience for there, not the paper. In the paper, they smooth it. They do a lot of things that you don't even catch during that paper. I mean, what they did in that paper. But here you can probably capture in GitHub, capture exactly what they've been doing.
Yeah.
And that's good. Thank you. Appreciate that. Well, thank you very much, Eli. I don't want to hold
Yep.
to thank you. This is really helpful. Thank you for doing it. Thank you.